Welcome you all for the online class on Control Systems Engineering. In today's class, we are going to see the problems in block diagram reduction. How to reduce the given block diagram into a single block and how to find the transfer function of the block diagram. Okay. So the first question is obtain the closed loop transfer function C of S by R of S of the system whose block diagram is shown in figure. Okay, so here one block diagram is given. We are going to reduce this block diagram by applying the rules of block diagram reduction, and we are going to find the overall transfer function C of S by R of S, that is output of the system divided by input of the system, that we are going to find out. Okay, so now in the previous classes we have seen the different rules applied for this block diagram reduction. Okay, now we are going to apply the rules on this block diagram and we are going to convert these block diagram into a single block. Okay, so first we have to think, okay, which movement we have to make, okay, to reduce this block diagram. So here in this problem, there will be an 3 input summer. Okay, in the rules of block diagram reduction, there is no rule with 3 input summer. Okay, so first what we have to do is, in the question, if you have a 3 input summer, we have to split it into two number of 2 input summer. Okay, so first you have to draw the question here. Then after that, what reduction we are going to make, okay, that you have to put a dotted line. Okay, so around this summer we have to put a dotted line. That means we are going to perform an operation on this summer, or we are going to apply an rules of block diagram reduction on this 3 input summer. Okay, then after after writing this dotted line over this 3 input summer, what we have to do is we have to write the operation in the top. That is, in the first step, we are going to perform the splitting of summer. Okay, so here we have to write it as splitting summer. Okay, so now how will you split the summer? See here, I have given the formula. If you are having a 3 input summer, this can be split into two number of 2 input summers. Okay, so in the center, this is a main path. Always here you will be having a plus sign. So we can split it into plus plus as well as plus minus, two number of 2 input summer. Okay, so in this way we can split it. So similarly here also we are going to split this 3 input summer into two number of 2 input summers. Okay, so plus minus as well as another one plus minus. Okay, so we can draw two number of 2 input summers. Okay, so now after drawing this diagram, what we are going to do is then what we have to what operation we are going to perform on this block diagram to further reduce this block diagram. Okay, so for that what we have to do is, here by keeping this diagram as such, we cannot reduce this diagram further. Okay, that is, we cannot apply any feedback formula or parallel formula, etc. So what we have to do is, we have to think which movement we have to perform. Okay, so many methods are there to reduce the block diagram, so we can follow any one of the method. Okay, anyway, you have to apply the rules of block diagram reduction correctly, then only we can get the exact answer. Okay, so here we can move this branch point, this and branch point from here to here. Okay, so without performing any movement at this step, we cannot reduce this block diagram. Okay, so here we can move this branch point from here to here. If you are moving it from here to here, what happens? What's the rule? Moving a branch point after a block means in the corresponding branch, see here we have to put the reciprocal of the crossed gain. Okay, here we are crossing the gate G. So here in the corresponding branch, we have to include the reciprocal of the gain, that is 1 by G. So in this problem, while moving the branch point from here to here, we are crossing the gain G3. Okay, so what we have to do in the corresponding branch here, we have to write the reciprocal of the crossed gain, that is G3. So here you have to include 1 by G3. Okay, so this will be the reduction. Okay, after putting this dotted line, what we have to do is in the top you have to write the operation, that is we are going to move the branch point. Okay, moving a branch point. Next, so after moving the branch point from here to here, what we have to do, we have to include 1 by G3 in the corresponding branch. So this will be the diagram. Okay, now what we have to do is further reduce the block diagram, what we are going to do or what operations we are going to perform. Okay, so now these two blocks are in series. Similarly, these two blocks are in series. So we can combine these two blocks. Okay, when two blocks are nearer by, we can combine the two blocks into a single block. Inside that we have to write the multiplication of the gain, that we know. That is also one of the rule. Okay, so now we can combine these two blocks. So what we have to write here, combining the cascaded blocks or series blocks. Okay, so here the two operations are performed at a time. Okay, otherwise first we can combine these two blocks, then in the next step we can combine these two blocks. Okay, here at the same step we are combining these two blocks. Okay, after combining this, what will be the diagram? This will be the diagram, that is G2 into G3 will be the value which is present inside the block, and here H1 into 1 by G3, that will be H1 divided by G3. Okay, so now this will be the diagram. Now again we have to see what further reduction we can make on this diagram. Okay, so here there will be a branch point uh, uh, other than the main path. Okay, so this is a main path. In the main path you will be having a number of branch points. Okay, here you will be having a branch point, and here there will be a summing point, summing point, summing point, and branch point, etc. Other than the branch point, other than the main branch, here there will be a branch point which shows that this gain is given to this summer, and also the same gain is given to this summer. Okay, so what we have to do is we have to split this into two loops. Okay, that is from this branch point H1 by G3 is given here. Similarly, from this branch point we can give this H1 by G3 to this summer. Okay, so we can write it as a rearranging of branch point. Okay, this operation you have to put it as a dotted line here. Then here you have to write rearranging of the branch point. Okay, in the next step we are rearranging the branch point. That is from here to here there will be a branch with the gain of H1 by G3. Again from here to here there will be a branch with the gain of H1 by G3. Okay, so now we can easily apply the formulas. Okay, so now again we have to see what operation we are going to perform. Okay, simply we can say this will be a feedback path. Okay, because the signals are flowing in the opposite direction. Here in this branch the signal is flowing from input to output. In this branch the signal is flowing from output to input, that is in the backward direction. So this will be an feedback path. So here I am giving the formula for the feedback connection. Okay, so if this is the feedback, then the answer can be written like this: feed forward gain divided by 1 plus, because here we have minus, into G into H. Okay, G into H. Okay, so similarly when we are reducing this feedback path, what will be the answer? G to G3 divided by 1 plus G to G3 H2. Okay, that will be the next diagram. So this will be the value of gain after applying the formula for negative feedback. Okay, so now again we can reduce this. Okay, so if you are considering this loop, this will be again a negative feedback. So this is the formula which is given here for negative feedback. This is the formula. So similarly we are going to apply the formula. So in applying the formula for negative feedback, it will be a big expression. See here, when we are applying a formula for negative feedback, this will be the expression: G2 G3 divided by this and feed forward gain divided by 1 plus G2 G3 H2, the whole divided by 1. Here we have minus sign, so here you have to put plus. this G2, G3 divided by 1 plus G2, G3, H2 into this feedback gain, H1 divided by G3. Okay, so all these values should be written inside a single block. Okay, so this will be an one big expression, isn't it? In the numerator, you have an numerator and denominator. In the denominator also, you'll be having a numerator and denominator. So we have to simplify it. Okay, after simplifying this, we can replace this whole block by means of a single box. Okay. So now in the numerator, no need to take the LCM. In the denominator, here we have 1 plus. So we have to take LCM. Okay, you know how to take LCM. Okay, LCM is 1 plus G2, G3, H2 into G3. Okay, now we have to multiply this LCM with 1 here and then plus G2, G3, H1. Okay, so always by applying the formula for feedback, uh, there is a possibility of cancelling the numerator as well as denominator terms. Okay, here 1 plus G2, G3, H2 as well as 1 plus G2, G3, H2 is present in the numerator and also in the denominator. So we can cancel these two terms and we can bring this G3 to the numerator. Okay, so if you are bringing the G3 to the numerator, in the numerator there will be a possibility of square term, that is G3 square. Okay, so you should remember this always. In the answer for block diagram reduction, you will not get a square or cube terms. Okay, which means that there is an excess term in the denominator. Okay, so here in the numerator there will be a possibility of square, which means that there will be an excess G3 in the denominator. Okay, so in the same step itself, we have to find out the excess term and we have to cancel that. Okay, so in some problems, that is in some rare situations, you will be getting the square term like this. Okay, if you are getting a square term, then immediately you have to cancel the common terms. Okay, so now in the denominator G3 is common, so we can take G3 outside and we can cancel this. Okay, now what about the expression G2 G3 divided by 1 plus G2 G3 H2 plus G2 H1. Okay, now we are going to replace this box, that is summer two blocks by means of this value G2 G3 divided by 1 plus G2 G3 H2 plus G2 H1. Okay, so that is the next block. Okay, now again here we have one G1 and also two blocks. We are going to again further reduce this diagram. Okay, now we can combine these two, isn't it? Because these two are in series or cascade. So we have to put the dotted line here. Then at the top you have to write the corresponding operation, cascading of blocks. Okay, so when we are cascading these two, that is when two blocks are nearer by or in connected in series, we have to combine that two blocks. Okay, or we have to multiply the gain. Okay, when we are multiplying the gain, we are getting the expression like this. Okay, so now what we have to do, again we can apply the formula for feedback. This is a positive feedback. Okay, so this is the formula given here for positive feedback. So if you are having positive sign in the formula, here you'll be having a negative sign. Okay, the forward path gain G, feedback gain H. Okay, so forward path gain divided by 1 minus, because here it is plus, then forward path gain into feedback gain. Okay, so based on this formula, we can write this as the forward path gain here is G1, G2, G3 divided by 1 plus G2, G3, H2 plus G2, H1. Okay, the whole value. This value divided by 1 minus the whole value, forward path gain into feedback gain, H1 by G3. Okay, so now again this is a big term, so we have to simplify this. Okay, by taking LCM. So here in the denominator we can take LCM and we can cancel the common terms. Again in the denominator you will be having one more term, that is G3. We can bring it to the numerator. So when we are bringing this G3 to the numerator, there is a possibility of square. Okay, so immediately we have to find out that term from the denominator and we have to cancel it. Okay, now we can cancel G3 and the answer will be 1 G1 G2 G3 divided by this value. Okay, now instead of this whole block, we can write it as an single block like this with the gain of G1 G2 G3 divided by 1 plus G2 G3 H2 plus G2 H1 minus G1 G2 H1. Okay, now that is the next block diagram. Okay, so this will be the next diagram. Now again we are having an parallel connection. So these two are in parallel because summer is at the output, that is at last, and also along the two paths the signal is flowing in the same direction. So which means that two blocks are in parallel. When two blocks are in parallel, listen here, here when two blocks are in parallel we can directly add the gain. Okay, so here we can add these two gains and we can replace it by means of a single block like this. Okay, so here in the formula, two blocks as well as one summer, both all are combined into a single block. Okay, similarly we can combine all these into a single block like this. Okay, so now the answer will be C by R. Output by input will be equal to the value which is present inside the block. Inside the block we are having the expression like this. Now we have to simplify this. Okay, so for that we have to take LCM and we have to multiply all the terms inside the bracket. Okay, then we are getting the expression like this. This will be the transfer function C by R of the given block diagram. Okay, in this way, by applying the rules of block diagram reduction on the given block diagram, we can find the overall transfer function of the system. Okay, then the next problem, using block diagram reduction technique, reduce the following block diagram. So here one block diagram is given, we are going to reduce this uh, and we are going to find the transfer function of the system. Okay, so here what we have to do is input as well as output and all the gains are represented in the frequency domain, that is of S, G1 of S, G2 of S, G3 H2 of S, H1 of S, etc. Okay, so all these gains are in the frequency domain, that is why it is given as a function of S. Okay, so always you will be having the of S, but simply we are writing it as G1, G2, H1, H2, etc. So in the question, if it is specified as G1 of S, G2 of S, etc., then you have to write all the gain with the of S. Okay, now what we have to do is we are going to simplify this expression. So here uh, similar to the previous problem, here also we are having a 3 input summer. Okay, we have to think and decide. Without splitting this 3 input summer into two number of 2 input summer, we cannot further reduce the diagram. Okay, so for that initially we have to split the summer. So first we have to draw the same diagram here. Then we are going to split this summer, isn't it? So for that we have to put the dotted line around the summer, and here also you have to write it as splitting of summer. Okay, we know the rule how to split the summers. If you are having one 3 input summer, that can be splitted into two number of 2 input summers. Okay, now this can be splitted into plus plus as well as plus minus. So similar to this, we can split this summer into plus plus as well as plus minus two summers. Okay, based on this rule. Okay, so now what we have to do? Now directly for this loop, we can apply the formula for negative feedback, isn't it? So this is directly similar to a negative feedback. Okay, so here you have to put the dotted line and here you have to write elimination of feedback. Okay, now what's the formula for negative feedback? Here it is given G divided by 1 plus G into H. Here we are having a negative feedback, so here you have to put plus. Okay, so the answer will be G2 of S divided by 1 plus G2 of S into H2 of S. That will be the next diagram. Okay, so this is the simplified value. Okay, this can be written within a single block. Okay, so now again we have to check or how to reduce this diagram further. Okay, so here by keeping this diagram as such, we cannot apply any rules. Okay, again we have to make a movement because in this diagram two loops are overlapping, that is this G1 of S with this branch. This forms an parallel connection. Okay, because in both the branches the signal is flowing in the same direction. Okay, similarly this block as well as this H1 of S, this forms a feedback connection because here the signal is flowing in the forward direction, here the signal is flowing in the backward direction, but both the loops are, this parallel as well as this feedback loops are overlapped. Okay, so what we have to do, we have to separate this parallel block as the parallel blocks as well as feedback block. Okay, so for that what we have to do is we have to move this summer from here to here. Okay, so if we are moving this summer from here to here, we have a formula, moving a summer after a block. Okay, so we'll moving the summer after a block, what adjustment we have to make? Listen here, so here we'll moving this summer after a block, in the corresponding branch we have to directly write the crossed gain. Okay, here we are crossing the gain G, so in the branch we have to put the gain G. Okay, similarly here also we are crossing the gain G1 of S. Okay, so in the here the branch involved is this branch, so in this corresponding branch we have to include this G1 of S. In this way we can move this summer here. Okay, now again it is overlapped. Okay, if we are interchanging the summer, we can easily separate both the loops, that is parallel loop as well as feedback loops. Okay, so now what we have to do, we have to interchange this summer. Okay, so how to interchange this summer? So before interchanging the summer, here two blocks are in series, isn't it? So combining cascaded blocks, here we can put the dotted line, and the next diagram will be like this. By multiplying both the gates, we can draw it like this. Okay, now again we cannot apply the formula for feedback as well as parallel loops. So this one parallel loop and this one feedback loop, again it is overlapped. Okay, only when the interchanging of this summer we can separate both the loops separately. Okay, so here this is the formula for interchanging of summers. Okay, so listen here, if two summers are nearer by, without any alteration we can interchange the summer. Okay, when we are interchanging the summer, there will not be any variation in the answer. Okay, that is already proved. Okay, so now based on this formula we are going to interchange these two summers. Okay, so if we are interchanging these two summers, the answer will be like this. Okay, so while performing the interchanging operation, here you have to write interchanging summing point. Okay, and here also you have to put the dotted line. In the next step you have to interchange the summers. Okay, like this. Now this will be the block. Now again we have to reduce this diagram. So here it directly represents the feedback, negative feedback, isn't it? So elimination of negative feedback. In the top we have to write like this. Okay, so now in this negative feedback we can apply the formula, isn't it? So the formula is given here. For negative feedback, what's the formula? Feed forward gain G divided by 1. Here it is minus. So here you have to put plus forward gain into feedback gain. Okay, G into H. Okay, so instead of this block, we can apply the formula. Okay, so when we are applying the formula, it will be a big term. That is like this. The forward gain divided by 1 plus forward gain into feedback gain. Okay. So in the numerator, you will be having a numerator and denominator. In the denominator also, there will be a numerator and denominator. So we have to apply, we have to take LCM and we have to simplify it. Okay. So numerator will be as such. In the denominator, if you are finding LCM, we are getting the term like this. Okay. You know how to find LCM. Okay. Now we can cancel these two terms and you will be getting the term like this. Okay. Now instead of these negative feedback loop, we can replace this expression. Okay. So the next diagram will be like this. Instead of the negative feedback, we can write the expression inside a single block. Okay. Now again we have to see how to reduce this diagram further. So here if you are seeing here, this will be a parallel loop. Okay. So here in this loop, the signal is in the forward direction. Here also there will be an in the feed forward direction. Okay, in the same direction. So this is the formula how to combine two blocks when two blocks are connected in parallel. Okay, this is the formula. That is, it is enough to add both the gains. Now here there is no gain, isn't it? That means the gain is 1. Okay, so here the gain is G1 of S. So what we have to do, we have to add both the gains. Okay, here you will be having plus and here also plus. Okay, that's why here we are writing it as 1 plus G1 of S, or we can write it as G1 of S plus 1. Both are same. Okay, suppose in the top you will be having a minus sign. Here you have to write it as G1 of S minus 1. Okay, so here if you are having plus, here also you have to write it as plus. Suppose if you are having minus sign here, correspondingly for the corresponding term we have to put a minus sign. Okay, that is very important. The next again further we can reduce this diagram. Okay, so now two blocks are in cascade or series, so we have to write combining the cascaded blocks and you have to put a dotted line like this. So if we are combining these two, we have to multiply the gain, isn't it? So correspondingly we can multiply both the terms. Okay, now in this way we can reduce the block diagram into a single block, and the output by input, C of S by R of S, will be equal to the value which is present inside the block. Okay, now here you will be having a bracket, so we have to multiply this inside the bracket. Okay, finally the answer will be like this. The final answer should be a simplified answer. Okay, the multiplying inside the bracket and by performing all the operations, you have to write the simplified answer as an final transfer function. Okay. The next, this is the another one problem. Using block diagram reduction technique, find the closed loop transfer function of the system whose block diagram is given below. Okay, so here one block diagram is given similar to the previous problems. We are going to reduce this block diagram using block diagram reduction technique, and we are going to find the transfer function of the system. Okay. So this is the given block diagram. Okay. So by keeping this block diagram as such, we cannot apply any of the rules. Okay. So anyway, we have to make a movement. Okay. We have to move either branch point or summing point before or after a block based on the rules we studied. Okay. Then only we can apply the formula of block diagram reduction. Okay. That you have to think and decide. Okay. So in this problem, we are moving this branch point from here to here. Okay. When we are moving this branch point from here to here, imagine these two will be in series and this is again a parallel connection. Okay. We can easily reduce this. Okay. So otherwise, many methods are there. Okay. Without moving the branch point from here to here, we can move this branch point from here to here. So when we are moving this branch point from here to here, again this form an parallel connection. Okay, and we can add this G3 as well as G4. That is another one method. Okay, and we can continue that. Finally, you will be getting a same answer. Okay. So now here we are moving the branch point from here to here. So when we are moving the branch point from here to here, what we have to do, we have to put the dotted line here, and correspondingly here you have to write moving a branch point before a block. Okay. So now while moving the branch point before a block, what's the formula? We have to put the corresponding crossed gain in the branch. Okay. So here the branch involved is this branch. In this branch, we have to put the corresponding crossed gain G. Okay. So here we are crossing the gain G2, isn't it? So in the corresponding branch, here the branch involved will be this branch. Okay. In this branch here, we have to include the corresponding crossed gain G2. Okay. So directly we can write the crossed gain here. Okay. Now again we have to think for the further reduction of the block diagram. Okay. So now after moving this branch point, further how will you reduce this diagram? So here again these two blocks are in series, isn't it? So we can multiply these two. These two blocks are in series. So we can multiply these two. Okay. And also this block will be a parallel connection, isn't it? After multiplying these two, here you'll be getting a single block G2, G3. This G2, G3 will be in parallel with G4 because these two are in the same direction. Signal flow in these two branches will be in the same direction. So we can add both the gains. Understood? So that's why three operations are performed in this step. These two combining the blocks in cascade as well as this eliminating the parallel blocks. Okay. So the next diagram will be multiplication of these two gains H1, G2, multiplication of these two G2, G3, and also adding of G2, G3 with this G4. Okay. So this will be the next diagram. So multiplying these two and multiplying G2, G3 and then adding it with G4. Okay. So now again we cannot apply the rules of block diagram reduction because here there will be a two feedback loop. Both are overlapped. Listen here, G2, G3 plus G4 and H2. These two forms and feedback, isn't it? But here there will be an disturbance. That is nothing but branch point. Okay. Either we can move this branch point after this block. If you are moving this branch point after this block, for this loop we can apply a formula for negative feedback. Okay. Otherwise, what we have to do, we can move this summer here and we can interchange both the summer. In this way, we can bring one of the loop inside another loop. Okay. So now two loops are overlapping. That is this G2, G3, G4 plus G4 and H2. This is a negative feedback. This is overlapped with G1, H1, G2. This is also a negative feedback. Okay. Both are overlapped. So we have to separate this. Okay. So for that, either we can move this branch point from here to here. So in the corresponding, when we are moving this branch point from here to here, in this corresponding branch, you have to make an adjustment. Okay. That is the reciprocal of the gain. This crossed gain should be included here. Otherwise, similar to this problem, we can move this summing point before a block. Okay. While moving the summing point before a block, what adjustment we have to make? that is in the branch, corresponding branch, we have to include the reciprocal of the crossed gain. Here we are crossing the gain G, so the reciprocal of the crossed gain should be included in the corresponding branch. Okay, so similarly here also, when we are moving the summing point from here to here in this branch, this is the branch involved, isn't it? In this branch, we have to include the reciprocal of the crossed gain. Okay, reciprocal means it is 1 by G1. Okay, see here in the next diagram, after moving the summing point in the corresponding branch, we have to include the reciprocal of the crossed gain. Okay, all the remaining part of the problem will be same as the previous. Okay, we have to copy that. Understood? Now what we have to do? Now we can interchange the summing point. If you are interchanging the summing point, one negative feedback will be inside the other negative feedback. Okay, so here we have to interchange the summing point, and here also there will be a branch point. Okay, two number of branch point in a single point. So we can separate this into two branches or two loops. Okay. So in the next step will be, that is interchanging of summing points. When there is two summers nearer by, without any alteration, we can interchange the summers. Okay, that is the rule. See here, when two summers are nearer by, without applying or without changing the any gain, we can directly interchange that summers. Okay, so similarly here also we can interchange the summers. When we are interchanging the summer, it will be like this. That is, this H1 G2, this term will be an inner loop. H1 G2 will be an inner loop, and this summer will be outside, isn't it? So 1 by G1 into H2. Okay, that loop will be an outside loop. Okay, so here 1 by G1 into H2, that loop will be an outside loop. Understood? Now what we have to do here, from the single branch point, it is going to this loop and also this loop. So separately, all these are same points, isn't it? So from this point, we can give the signal to this loop, and also we can give the signal to this summer here. Okay, so now this will be the diagram. Now what we have to do here, this will be a negative feedback. Now we can apply the formula for negative feedback. So here I have given the formula for negative feedback, that is forward path gain divided by 1 plus forward path gain into feedback gain. Okay, so instead of this, we can write it as G1 divided by 1 plus G1 H1 G2. Okay, after reducing this into a single block, that block will be in series with this G2, G3 plus G4, isn't it? That's why here also we are putting a dotted line. Okay, so we can combine these two gains. Okay, that is, we have to multiply both the gains. Again here there will be a cascading of blocks. That is, two blocks are in series. So the answer will be H2 by G1. Okay, that is 1 by G1 into H2, which means that H2 divided by G1. Okay, so the next block diagram will be like this, H2 by G1. Here, after applying the negative feedback, you will be getting the answer like this, G1 divided by 1 plus G1 G2 H1. Then that block is in series with the G2, G3 plus G4. So we can combine both, isn't it? So after multiplication, you will be getting a block like this. Okay. So now what we have to do is, again, we have to see how to reduce this block. So here it is a negative feedback. So this is the formula used for negative feedback. Directly we can apply the formula. When we are applying the formula for negative feedback, it will be a big expression. That is, this and feed forward gain. This and feed forward gain divided by 1 plus, because here we have minus sign, so here you have to put plus. Okay, feed forward gain into this feedback gain, H2 by G3. Okay, so now what we have to do, we cannot write this value inside a single block because this is a big expression. The numerator itself, we have a numerator and denominator. In the denominator also, we have a numerator and denominator. So we have to simplify this and we have to go for a next step. Okay, so now in the numerator can be as such, in the denominator we have to take LCM. Okay, when we are finding LCM, you know how to find LCM. It will be like this. Okay, now we have to cancel the common terms and the expression will be like this. Okay, so now what we have to do, we have to write this term instead of this block. Okay, instead of this block we can write this term. Now this will be the next step. Okay, so further how will you reduce this block? That is, this is a negative feedback. Now we can apply the formula for negative feedback. This is the formula for negative feedback, isn't it? So here, when we are applying the formula for negative feedback, forward path gain divided by 1 plus forward path gain into feedback gain. Feedback gain here is 1. Okay. So now here it will be forward path gain divided by 1 plus forward path gain into feedback gain, that is 1. Okay. Now in the denominator again we have to take LCM and we have to cancel the denominator, and the answer will be like this. Okay. Now this can be replaced, that is we can write this value inside a single block. Okay, that's a final diagram. Now the input will be R of S and the output will be C of S. We can write the transfer function as output divided by input C by R. That will be equal to the value which is present inside a single block. Okay. So in this way we can reduce the given block diagram into a single block, and hence we find the transfer function of the block. Okay. So now these are all the homework problems. Okay. So the first problem, we are going to reduce this block diagram into a single block. Okay. So here also we have to think which movement we have to make. Okay. To apply the rules of block diagram reduction. Okay. Here without any movement, directly we can apply the formula. Okay. See here. This is a parallel connection. Here the gain is 1 and here the gain is G3, because in both the branches signals are going in the same direction. Okay. So we can reduce this into a single block. So similarly, by applying the rules of block diagram reduction, we can reduce this block diagram into a single block. Okay. The value which is present inside the single block represents the transfer function of the given block diagram. Okay. Now the second problem will be here. This is the question. We are asked to find the transfer function, or you have to reduce the block diagram. Okay, both are same. Now in the summer, normally the that is the sign will be inside the block, isn't it? But here it is given outside the block, so we can write it inside the block. Okay, so here the sign is plus, so inside this we can write it as plus. And here the sign is minus, so inside this we can write it as minus. Okay, and here also outside the summer the signs are given, so here it is minus, isn't it? So inside this we can write it as minus, and here inside this it will be plus. Okay, and we can easily solve this. Here also two loops are overlapped, so similar problem we have seen already. Okay, that is here this is a parallel connection, that is G1 as well as G3 are in parallel, and this will be a feedback connection, G2 as well as H1, both are overlapped. So what we have to do, we have to move this summer here, and we have to interchange this summer, and we have to separate the parallel path as well as feedback loop. Okay, after that we can easily apply the rules. Okay. Next problem will be, this is one of the university question. So here also we are going to reduce the block diagram. Okay, by applying the rules of block diagram reduction. Okay. So after finding the reduced block diagram with the single block, the value which is present inside the block represents the transfer function of the given block diagram. Okay. Okay. Thank you.